Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar lecture theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar. Friends, welcome to the 15th lecture on the course Maritime Structures under Fire, Blast and Explosion, which is offered by IIT Gandhinagar under the braces of Swayam Prabha. This 15th lecture, we are going to discuss about the damage estimate under fire and explosion and also to learn about some of the effects of fire and explosion on structures. Because so far we have been learning the characteristics of fire, explosion, how they will occur, chemical combustion reactions and how to control them. Slowly we will get into fire structural engineering where we will also talk about what are the consequences of this fire and explosion on structures. So, as a continuity of what we discussed in the last lecture, we said flammability diagrams are a useful tool to control fire. Once the flammable region is established for a particular fuel mixture, then one can always use this as an effective tool to avoid fire accidents. This can be done by one of the following ways. You either admit or allow more fresh oxygen into the containment, which shall now reduce the concentration of fuel mixture. Friends, remember, this is only when it is fuel controlled fire. If it is ventilation controlled fire, this cannot happen. So, usually in hydrocarbon industries, accidents are generally fuel controlled. Therefore, allow more fresh oxygen and reduce the fuel mixture concentration. So, what happens is, when you allow this, when the fuel mixture concentration changes, then it gets diluted, when the concentration decreases, then there is a subsequent change in the limits, flammable limits of the mixture, and flammable region will now converge very sharply. You can replot this and see if the flammable limits are changed significantly because of the reduction in the fuel mixture concentration, you will notice that the flammable diagram nose and the flammable region gets contracted. Okay. The other option could be change the working temperature. We all know that AIT and flash points are function of temperatures. Change the working temperature of the containment, which can also influence the limits. We already saw how the flammable limits are influenced by increase in temperature. So, change the working temperature and then also influence or change the limits. Therefore, friends, flammability diagrams help us giving first hand information about the fire accidents to safety personnel, which can also help us to control fire accidents before it happens, or at least limit them to some extent, so that we can alter the flammable region of the mixture such that the fire avoids sustainable growth and then burning states. One can also estimate the damage under fire and explosion. Let us see how we do it. In explosion damage scenario, it is a very common practice to estimate the scaled distance of the explosion energy, how far the explosion energy can spread or propagate, scaled distance. So, what you do? Let us first compute the flammable inventory present in the scenario. This can be easily computed, what we call as a fire load. If you know the mass which is participating in the explosion, one can find the total mass of the flammable fuel. If I know that, can always find out the scaled overpressure, computing this equation. The scaled overpressure can be computed from this equation if I know the atmospheric pressure. Then I can always estimate the overpressure from this equation, where the scaled distance ZE is known to me. So, once I know the scaled distance, I already did a problem in the last lecture, please refer to that. If we know the scaled distance, depending upon the overpressure, which can be computed using this equation, if we know the overpressure, from the overpressure I can always qualitatively look at the damage, which can be also quantified to some extent. If the overpressure is about 0.28 kilopascal, you will only hear a loud noise and glasses will break. If the scale overpressure touches 75, it can cause human fatality. So, one can relatively find out what is the consequence of the explosion in terms of damage that could cause the human and buildings and structures, etc., based upon the scaled overpressure, which can be computed if I know the scaled distance. Okay. So, scaled overpressure is also the pressure computed from the scale distance. I can use this equation for doing this. Having said this, let us now move on to a very important understanding of fire which has happened in structures. Let us say this is a fire engineering laboratory, a dedicated laboratory what we have in IIT Gandhinagar. You can see the building, the full scale building of 2-story, which is also set to fire to understand the real time scenario and behavior of structural elements under fire. So, when this happens, in just 2 minutes, it's a time scale what we are showing you here. In just 2 minutes, the flame spread into the ground floor compartment. The curtains provided in the compartment all catches fire. In the next third minute, maximum temperature ground floor reaches 550. So, all the glass panels present here starts breaking and falling. After 6th minute, the local failure of cement board, which is used as beam protection at the ground floor, fails. So, fire spreads to first floor. In 10th minute, flashover took place in the ground floor. So, all the external excessive facades failed. In 15th minute, fire load at ground floor almost fully consumed, flashover happens in first floor. And in 17th minute, fire spreads to second floor. Friends, it is a very interesting time scale for you to understand how quickly fire spreads vertically and of course circumferentially. So, Professor Gaurav will discuss more in detail about this particular setup. He will also show you the video of this later in his lecture, and you will understand that the structural fire engineering is gaining momentum in industrial safety practices because the timeline with which it happens and causes devastation is a very important concern for all engineers. Having said this, let us talk about what are the concerns we have from fire about life safety. Let us say this is an elevation of a building, not the same building what I showed in the previous slide, it is a different concept, right. So, generally near the ceiling you always have smoke detectors and you have vents to release smoke and gas. Firefighting systems are placed as a part of this. There are also sometimes smoke ducts provided in every floor near to the ceiling so that the smoke can escape through this vent. It can be either artificial or what we call mechanical ventilation, can be natural also. You will see in most of the high rise buildings, when the floor height is very large, let us say 4 meters plus, you will always see there are ventilators provided near the top. There are two reasons for this. One, these ventilators will cool down the air inside the room and the room will remain cool, and also this acts as a fire ventilation or the smoke ventilation in case of fire. So, it is very important now to learn that in case of fire, to have an effective escape planning, you should think about and plan about good sizing of the corridors, because the people will start escaping from this only through the staircase, because lift cannot be used during fire. There is a note given, do not use lift during fire. So, people do not use lifts. So, they used to use the escape corridors which is provided at one end of the building. So, we must then avoid loading these corridors, and these corridors should have good sizing, and you should design the staircase location, rise and tread in such a manner they are comfortable to get up and get down, walk up and down easily. Okay. Usually they cannot contain more than about 10 risers to step half of the floor, let us say 20 risers for every floor. Average. This is a schematic diagram, do not look at the scale here, the schematic diagram. We should also have enough provision for refuge areas. Refuge areas are the places where on the corridor people go and get dumped, they go and stay at the side stacks. We should also have enough smoke venting, as you see here, which will be connected mechanically and collected and removed out. Smoke venting. There are segments where positive and negative pressure areas can occur. We already saw how the negative or suction pressure causes damage during explosion. So, one should take care of this particular segments and also evacuate these kind of negative pressure segments easily, so that they get balanced with to maintain the pressure balance or the pressure areas which are caused because of impulse force caused from an explosion or fire. Having said this, friends, Kerber also did an analysis to explain the legacy of timelines between modern and the old structures. Let us say the modern fire timeline and the legacy timeline are compared here. In the modern timeline, the fire timeline where we use modern materials for construction like cellulose fibers, then wood dust, furnitures, lot of curtains, false ceiling, etc. In the modern fire timeline, there is a very shortest time to flash over, it happens very quickly. Whereas in legacy fire timeline, it takes some time to establish this. So, modern construction materials are quite dangerous because they can catch fire and there is a very shortest time to flash over. And the longest time to flash over is also very quick, whereas here it is about 35 minutes from the start of fire, but here it is very close, within 5 minutes you have the flash over. Then when you look at the time to collapse unprotected floors, it usually takes about 50 minutes, about an hour. Nowadays within 15 minutes, you have seen an example where in 17 minutes the ground floor and first floor got fired completely and the fire moved to the second floor. So, in modern fire timeline, the time to collapse starts is about, let us say, 12 minutes from the start of fire. Usually it used to be about 1 hour, 50 minutes, but no. When you talk about protected floor where fire insulation is done, then it can sustain till half an hour, even in the modern case. But in legacy fires, they used to sustain about 2 hours. Okay? But as you keep on using modern materials, false ceiling, contained space constraints, closed windows and roof fitted air conditioners, no ventilations for smoke and gas, etc., we have time to collapse of even protected fires is within about 30 minutes. So, one should evacuate people within 30 minutes maximum, beyond which rescue is not possible. Whereas this was extended to conventional buildings in olden legacy times, which takes about 2 hours approximately. So, the fire rating of structural systems has gone down drastically because of use of modern materials in construction. Kerber gave a good analysis of this, and thanks to him we acknowledge his work published in Fire Technology Journal in 2012. So, please read this paper for more details and learn the more details about why fire is a concern for structures. Now, as a structural engineer, let us see what are the main effects of fire caused. One of the effect which is serious about fire is thermal expansion, which is rising from uniform heating. Let us say I have got two examples here, which is unrestrained and restrained systems. In unrestrained systems like what you see here, a cantilever, when subjected to increase in temperature, the steel gets heated and gets expanded. It gets expanded because it is free to expand, and the temperature rise for a simple steel of 350 megapascal yield strength, it goes to about 175 degrees Celsius. And when it is unrestrained, it does not induce any additional stresses in the member. But when you restrain them to expand, then they will induce thermal stresses, which is actually a function of Young's modulus of steel and expansion, coefficient of linear expansion, thermal expansion of steel, and the delta T, to which this is subjected to the increase in temperature. So, this will induce what we call thermal stresses, which were not present when it is unrestrained. That is first issue. So, it induces thermal stresses in addition to the conventional bending, shear and torsional stresses in buildings for which they are designed. The second issue is it induces something called thermal induced buckling. In a case of restrained system, you also have thermal induced stresses. They will also create something called buckling force, which is a proportion of or proportional to this thesis, which is looked at pi square EI by relativity square, which also causes thermal induced buckling. So, one is thermal induced stresses, second is thermal induced buckling as well. The next one is it also causes something of thermally induced curvature. You must have seen when you heat a building or when you see a building post fire accidents, you will notice that the members, especially steel structures, have actually bent. Okay. Sometimes they are twisted also, they are warped also. So, this curvature which is caused on the member is not because of bending or loading, it is caused because of thermal temperature rise, which is different from both the sides of the member. So, if the member is let us say 500 mm deep, a steel structural I section, this surface is in fire or this surface not in fire, this in fire, and this temperature gradient between this surface and this surface causes additional curvature which happens like this. So, friends, we can quickly say the stresses, temperature induce additional stresses, it causes buckling, it also causes additional curvature, which are all to be addressed in fire resistant design of structures. Having said this, how this is counteracted in design? I will touch upon this very briefly in detail, later lectures will cover this. Let us look at the main effects of fire on structures. Eurocode handles this by allowing changing in material properties. Okay. So, basically this is the original curve in case of no fire. In case of fire, this curve is modified this way. So, the modification on concrete at different temperature with siliceous or calcareous aggregates are given in this equation or in the table form. Okay, this is available in Eurocode. We will take up an example later, and using MATLAB will help you out to find out the thermal gradient difference between the point which is exposed to fire on a beam and between the point which is not exposed to fire on the same beam. We will plot the temperature gradient in a design example and show you later how this can be computed. Let us see what is the main effect of fire on structures. Without fire in the design, we have got good margin of safety, be it any design method, be it elastic design, plastic design, limit state design, we have a good margin of safety. But with fire, this margin of safety reduces in two ways. One, there is increase in stress and strain, as I said, thermal induced stresses. There is decrease in allowable strength at high temperature, because we already saw the properties of material. For example, steel degrades, strength degrades, yield strength degrades as the temperature increases. So, there is a decrease in strength, there is increase in stress, both of them together eats away this margin of safety. That is a serious concern in design. So, one of the direct impact of fire on design is there is a good reduction, compromise on margin of safety in design, because there is increase in stresses caused by thermal variations, there is decrease in strength of the material at higher temperature. Both of them put together decreases the factor of safety or margin of safety which usually be present in the design. So, what is this reduction compared to this with an example? We will explain later in coming lectures, but the concern is this. So, friends, let us visually see what are the effects of fire on structures. So, this is study conducted by Lindsay et al., published in 2012 on thin wall structures. The reference is available here. I would strongly advocate and recommend that you please go through this paper to understand more in detail. I am only showing the conceptual part of this as we understand from this particular paper. So, according to Lindsay et al., you know, concrete structures when set to fire show instability effects. Okay. Especially this study was conducted on steel structures, is fire safety analysis and 3D framed based on full scale fire test. So, steel structures show lot of instability effects. That is number one observation made. The second is they undergo large deformations. There are some permanent deformations which are otherwise referred as plastic deformations. So, all these are observed on a full scale test conducted in steel and concrete. For example, let us look at the concrete structures which is done by Abbasi and Hogg in 2006. The reference is available here. In concrete structures similarly, it also creates instability effects. It also imposes large deformation. It also shows permanent damage. In addition to that, it also shows spalling of concrete, what we call as fire induced spalling. Concrete withers off at high temperature and enables steel to directly get exposed to fire. Okay. Both steel and concrete structures are equally vulnerable, equally worrying when they are subjected to high temperature or let us say fire and explosion. If you look at effect of fire closely on concrete structures, spalling is a very serious issue. Okay. So, there is a notch for splitting, this becomes a saturated zone, then the zone over 100 degree starts showing spalling front and concrete spalls at high temperature. Okay. The photograph shared by Robert Johnson is acknowledged, which can give me a clear visual effect of how spalling takes place at high temperature in a larger macroscopic view. Furthermore, friends, spalling is more serious that the whole cover concrete completely gets removed and steel is fully exposed. Steel is completely exposed. See this column under fire. So, friends, in this lecture we learned the effects of fire, we also learned how to compute the damage estimate under explosion. For example, if I know how to compute the scaled distance, if we can also compute the peak overpressure, from this with the help of a table given in the literature, I can always compute for a specific value of overpressure what is the relevant damage to structures as well as human. We understood this. We have also understood what are the visual effects caused by on structures due to fire, why fire is a botheration in structural design. The factor of safety or the margin of safety gets reduced because of increase in stresses, thermal stresses, and because of decrease in strength at high temperature. These two put together decreases the factor of safety margin available in the design. Therefore, the design becomes more vulnerable to failure. That is what we understand. Therefore, friends, fire and explosion resistant design becomes inevitable not only in maritime structures, of course, all industrial structures which deals with flammable chemicals, etc. However, friends, for maritime structures, we are dealing with oil and gas exploration or oil and gas stocking, processing plants, etc., or even port and harbors where LNG, CNG terminals are handled. Therefore, we are more vulnerable to this kind of damage scenarios, and therefore, maritime engineers should be aware how to design the structural systems, be it steel or concrete, for existing or known fire scenarios, and also plan the emergency response planning for fire rescue operations to save asset and personnel involved in the specific operation. Thank you very much. Namaste.